forget which one, C14. There it is. C14 is formed at a certain rate in the upper atmosphere. And when you're alive, you have that same ratio of C14 to the other carbon atoms in your body. When you die, you're not making fresh cells. The C14 keeps on decaying. The ratio of C14 to C regular carbon decreases. So what you know is N0, it's assumed to be a certain number. They always put that in the problem. And I always say, how do they really know that that's the number? Because maybe one year the sun was really active and we made 10 times as much C14. But they always say, well, you can figure that out by looking at the growth rings on the tree, and if a bunch of trees died out at a certain time, you know for that span of time it wasn't that constant rate. So geologists have all these arguments that you just have to go along with it. But that is the weak point. Okay. But it does work, and that's how they do it. So they know the rate constant for it. In other words, in this table I was just looking at that I showed you a few seconds ago, gives the half-life. So you can figure out, just like this, you can figure out the rate constant. If you know the original number of C14, the regular 14 in the body, or the piece of paper, or the bone, or whatever, you measure the new ratio, you plug that in here, you can tell how long ago the thing died. You can do the same thing with rocks. Apparently there's certain things like potassium that decay at a certain rate, and they can work backwards and figure out what the radioactive potassium was a long time ago. They picked potassium, but I think the half-life is 10 to 8 years, something like that. 10 to 8 years. Anyhow, it's all the same. It's all based on these same three equations. Okay? So calculations dealing with radioactivity are really simple. The other thing I can do is tell you what this ratio is. I could say after 25 minutes, N is 0.5 N0, 50% of N0. That means I told you this, I told you this. You calculate lambda, and then you work backwards to find the half-life. The problems go forward and backward. But that's all there is in nuclear physics dealing with radioactivity. Three basic equations, some redefinitions. Instead of talking about change in concentration or the rate of reaction, we now talk about the activity, but it's the same quantity there. We left the minus sign in here so we could do that calculation. We took it away there. But notice when he did the half-life calculation for the rate of reaction, and I said you can talk about half-lives for reaction, we just didn't bother doing it. You want to leave the minus sign in. We left that in when we did that calculation back there. Okay? Any questions about that? Easy, right? Of course it is. Just have to do 4 or 5 problems. I assigned the problems online with the web homework. You can work on those over the weekend. You work on that take-home quiz. Don't forget to pick up the take-home quiz before you leave. The last thing I'm going to do is finish out this lecture on nuclear chemistry. First of all, I'll ask any questions about what we just did. We're all set. Now here he talks about the radiocarbon dating, and basically you get this bombardment in the upper atmosphere, so you have a constant level of C14, and so this, when you're alive, you have a certain ratio. They can calculate, they know what it is, they always give you that in the problem. Then you take no more C14 or anything else is taken up, I guess, and so the ratio decays, so you start measuring the rate, the ratio, and you plug it into that equation. Here's another nuclear reaction. This is called fission. You have something like U-235, which is called fissionable material because it fissions or breaks up. So you hit it with a neutron, it gets excited, That's what that's supposed to show. Then it splits up, usually into a smaller and a larger particle. Something like barium and krypton are typical products. The important thing is, it produces more neutrons than it used up. That means the next 3 atoms that are sitting there do the same thing, and within a few millionths of a second you have a big hole in the ground. Okay? That's the basis for the atomic bomb. Makes a lot of energy because the mass of the particles here is much smaller than the mass, well not much, slightly smaller, but remember E is equal to mc squared, so if a little bit of matter disappears, it produces a lot of energy. The energy is in the motion of all these particles and the surrounding atmosphere and things, whatever they do. When you have a nuclear reaction or a nuclear reactor, it's just a fancy source of heat because heat is energy. That's what it says. Energy is in the form of heat. So down at San Onofre, what they did before they ran into trouble was that they did this. They ran water through it, made the water hot. The water goes out and drives your turbines, and you produce electricity to go into the grid. They found some leaky water, and so they stopped doing it. I live close by there, and so there are all sorts of different things. First thing they sent a couple of months ago was a package of iodine pills. Then you eat the iodine pills, and if there's radiation around, it absorbs it instead of going into or it goes in your thyroid. I don't know where it goes, but the iodine is supposed to protect you slightly. It's like my watch. I was happy with my watch. I'm still happy with it, but I don't wear it anymore. And I kept the iodine pills handy. But the idea is we think there's trouble, we drive away fast. Get in my way. Okay. So anyhow, the way they control these, by the way, is with something that absorbs neutrons. In other words, they keep this thing going at a certain rate to produce a certain amount of heat instead of a hole in the ground, and they do it by putting in neutron absorbers. The most common thing that absorbs neutrons is the element cadmium. So you have little rods of cadmium, and when they're controlling the reactor properly, they pull it out, it gets hotter, they push them in, it gets colder. And so they control the temperature very precisely. And they say in the case of an earthquake, the rods are supposed to drop in rather than shaking out. Okay? Apparently it didn't work in Japan because the thing got very hot. But you got to assume they know what they're doing. Sometimes they do and sometimes they don't. That's all it is. It's a fancy source of heat. The rest of the thing generating electricity is the normal way. Now the big problem for this, of course, is all of these particles are now unstable nuclides. And most of them have half-lives of 40 and 50,000 years. What do you do with it? You ship it at night to Nevada and hope they don't notice. Or Utah. And say, we're going to pay you a lot of money to put it in your salt mines. And they say, sure, any money coming in is better than none. Okay, so anyhow, that's where it's going. That's what the big thing is. So we have a lot of waste material sitting around that we're trying to get rid of. And somebody said, why don't we just put it in a rocket and shoot it into outer space? And of course, if we have an accident with a rocket, we'll distribute it uniformly over there, just like we had set off 5 or 10 atomic bombs or more. Because there's a lot of radioactive waste out there right now. Anyhow, in the middle of the night, if you're driving behind a car with one of those big purple triangles, a truck with one of those big purple triangles, you might want to pull over to the side of the road and let them get a good head start, or whatever you do. Okay, you don't want them behind you. Okay, so anyhow, that's one of the problems with the nuclear reaction. It does produce a lot of energy, and they can do it, and they can control it. There are some anomalies in the world, and sometimes we can't, but most of the time it's under control. But, and I'm certainly not going to move away from there. If they start up again, I'm not too worried. Okay, so coming back to that, that's nuclear fusion. I'm sorry, nuclear fission. I was looking at the wrong thing. Here's some more things about fission fraction. Notice it says you produce a lot of kilojoules of energy, which is equivalent to burning 3 tons of coal. And this is for what? Less than 1 gram of uranium, I think. Where does it say? Yeah, it's per gram of uranium you produce that much energy, which is 3 tons of coal per gram. Which you don't have to worry about. It's a lot of energy, but they don't have to burn the coal. Down here in Huntington Beach, they have that big power plant, and every so often you see coal trucks driving there carrying several thousand tons, or several hundred tons, I guess they aren't that big. But they carry several hundred tons, and you see trucks driving there 24 hours a day for a month, and they stack it up, and then they run the plant until they've used up all their energy credits, and then they shut it down unless they can buy some more, because coal burning things make more pollution in the air. But these are all different things. The next thing, here's nuclear fusion. You take two hydrogen, there's deuterium and tritium, and you bang them together and they make helium, and they make neutrons. And that has a large mass difference. You get a lot of energy out of one of those processes. Okay? The only problem is you have to have it really hot to start that. This is the foundation of the so-called H-bomb. And what they do is pack hydrogen, I assume, you can't take my word for it, but if you look on the internet, they'll tell you exactly how to do it. Anyhow, they take hydrogen and different nuclides of hydrogen, put it in a small core, surround it with a shell of uranium that is ready to fission, and when the right time comes, you push it all together, the uranium starts fissioning, everything gets really hot, and then this starts undergoing fusion, and it gets really hot. And now the hole that you make in the ground is about 20 times bigger. For the same size bomb. Fantastic. Okay? So what you do is you want to set ways of doing this. One of these things is some sort of a high magnetic field. That's the so-called tokamak. Those are all big fancy electromagnets. And what it's trying to do is confine the plasma of the hydrogen into a small volume so that it's at high temperature in the plasma state. It fuses. And they've actually had this going for like 10 to the minus 8 or 9 seconds where they were having it control fusion. Unfortunately, it takes so much energy to do that that they have to have it going for about 10 to the minus 6 seconds before they can make money out of it. They haven't been able to do that. Newer techniques, they're using cross laser beams and things like that with, again, not much success. It can be done, but you don't get more energy back than you put into it so far. But supposedly, the fusion process is supposed to be better. This is the process that's going on inside the sun. The only problem, again, it doesn't produce radioactive byproducts, but all that energy does cause nuclear rearrangements in the confinement material, and so you still have some radioactive particles to deal with. And here's some information about radioactive decay, and these are the different dose units that they talk about. The Curie is the basic unit, and it's the amount of radiation, or the number of disintegrations, which is called a becquerel. Disintegration per second is a becquerel. So 1 gram of radium produces 3.7 times 10 to the 10th disintegrations per second, so that's called 1 Curie. And as I said, a disintegration per second is called a becquerel. Where would you need this information? If you're on the $50,000 question, if you're on the $2 million question, they won't ask you anything that easy. Okay. So I'm just tossing that up there. So when people talk about grays, it's a unit of radiation. Sievert, the same thing. And REMS. These are the things. By the way, REMS is what you do when you're sleeping too. Okay. Coming back to this thing, what they do is so many units of this have been found to be hazardous to your life form or your body tissue, and you get cancer, whatever else you get. When it starts smoking, you're up in here somewhere. Much higher amount of energy. But small amounts staying in the tissue, cause cancers to grow, and eventually it gets you in the lung. Okay, questions? That's the complete lecture for Chem 1B. All the rest of it is lab work. Hopefully, if our ammonium sulfide doesn't come in this weekend as promised, I don't know what we'll do. We'll probably do the spectroscopy experiment. That's a messy one where you have to boil and dissolve metals with HCl, and then you have to dilute it, and then you have to make reference samples. It's not that tough. We do that used to do that as an experiment. until people got slower and slower, and now we're lucky to get through 5 experiments with the qualitative analysis. Okay, then I'm going to bring up reagents.